So we are done with the theory part of our scheduler. Now let's go ahead and kind of program it through. So what I have on the screen here is our the good old code that we have been, kind of trying out our assembly programs in. The, the code space is work environment. So what I'm going to do is get rid of all the useless files. So I'll just do make clean here. And so all the files are gone. The foo.s is the only one that we have. Now what we are going to do as part of this lesson is we're just going to program the SysTick timer and see whether or not the handler for that gets called correctly. And so when we would have, just a moment, yeah. So when we would have the SysTick handler executing, well, when we will have that, what we'll be sure of is we have a way, at least if the CPU is executing task 1, we have a way for it to be interrupted. That is pretty much it. That is what we will achieve. So we will just check whether or not it can go to the SysTick handler, and then from there return back here and move on. And we won't even have these tasks right now. We'll just start with the reset handler, and we'll kind of just program the SysTick and then kind of have this branch in place, right? We'll just loop in one place. So that is what we want to achieve. At the end of this lesson, we will have a way to program the SysTick in assembly and the fact that it will be functional. And then we'll make kind of, minute changes to it so that eventually the scheduler is implemented. Okay, so with this out of our way, there are some changes that we would need to make to this code here. First off, let's get rid of, everything within reset handler except this b dot. B dot is the for forever loop, the while one, so to speak. So our CPU, if it lands here, will spin in its place, right? So that's the idea. Now recall that, okay, so to be able to recall, we'll go to our readme file and you'll go to, or we will go to the Cortex-M3 devices generic user guide. This is the same one that we had explored in the previous lectures to get an idea of the SysTick and the exception entry and exit. All right, once we are here, we want to go to, well, the processor's peripherals, and within that, the SysTick timer, right? And we take a look at, well, actually, yes. So we'll just click on the system timer or SysTick, and then we get to see that these are the registers. So these numbers are useful to us because these numbers are the addresses. So let me also explain this a little bit. So we have SysTick here, the SysTick timer. Oh, well, actually, SysTick itself is system tick timer. So the way to program this is by modifying certain registers that are mapped on the memory, that are mapped as a memory address. So if we manipulate that memory address, we effectively are manipulating the SysTick hardware. And this idea is called the memory mapped IO. And pretty much all the modern processors and controllers use this. And the idea is very straightforward. There is an address associated with the register. So if you manipulate that address, effectively you are manipulating that hardware, right? And so what we see here then, these are the addresses corresponding to these registers, and then each of these registers, depending on which bit you manipulate, are going to influence the hardware. So that is the idea here. So somehow, obviously, we want to reach out to these memory locations. So we need to have a way in assembly to manipulate the memory. All right. Long story short, these addresses are useful to us. They're important to us in terms of programming the SysTick hardware. All right, so these addresses are important to us. And now what I'm going to do is we'll go back here. And the other thing we have to reason about is that when the SysTick um, kind of reaches the value of 0, it is going to fire an exception. The SysTick exception, which we, in the previous videos, we noted that it was at the address, or rather, it was at the location 15 in the exception vector table. So let's see the vector table. And then here we saw that the SysTick was at location kind of 15, right? So essentially then it is at this point, which is hex 3C. So what we are going to do then, we need to add an entry starting from, or rather, we need to add an entry, a function pointer, so to speak, a label that holds the code for SysTick handler, and that entry needs to be put into the vector table, right? And this will become clear in a bit as we go ahead and, as we go ahead and explore a little more. What I'm going to do is cheat a little bit. I have few things copied over on the side. I'm going to paste those so I can avoid typing. What we are saying is, so first thing is the stack pointer that we don't have a problem with. Then we have the reset handler's address, which is this, which is perfect. Then we say, hey, now skip ahead and go to the address of hex 3C and put the SysTick handler related address there. And so what I'm going to do is, we don't have SysTick handler right now. I just copy pasted it. I'm going to copy all of this and paste it here and change the reset handler here to SysTick handler, right? And so what we have now is, whenever this SysTick handler is fired, and how to fire it, how to program it, we haven't talked about it yet. So whenever it is fired, this is the function that gets called. This, so to speak, then is the ISR for SysTick handler, right? So the exception, if the exception fires, this is where the call will land, right? Okay. Now, what we are going to do is, we are sorted with the vector table thingy. We have that in place. And again, how did I know the hex 3C? I got it from here, right? And again, note that, oh, okay. Okay. Note that there are other handlers also here. So I'm just skipping those memory locations. I'm saying, hey, from here, now change the, so to speak, the place where the code needs to be put, change that to hex 3C. So that is what the .org does, right? So that kind of moves ahead and says, okay, now we have to start putting the code from this location. And what is the code? We put this, the function point, whatever the value of this is. That address goes in this memory location. All right, so that's then the .org directive. These are what we have seen. Now what we're going to do is optimize this a little bit, but we'll do that in due time. All right, so as part of the reset handler now, we are supposed to modify or program the SysTick handler. So what I'm going to do is take the code for that and essentially kind of put it here first, and then we will talk about what those values are. So first off, some more assembly related insights. So the way in C language we have the hash define, which lets you take a name, let's say ABC, and associate a value with it. So anywhere you use ABC, it'll be kind of replaced, a text replacement to the number 10. right? And it could be anything here, right? So ABC just gets replaced by whatever follows. So that was like the C way of doing text substitution. So in assembly, we have the .eq directive, EQU directive. And what this will do is you can have a friendly name here followed by a comma, and then you can have a value. So anywhere we use this string, so to speak, the SysTick underscore CSR, that will get replaced with this number. And essentially what we have here is I'm having friendly names that are mapped to the addresses of the registers that we saw here. So let me go ahead and again show you, right? So you see these numbers here, E000, E010, 14, 18, and 1C. So exactly the same thing mapped here, right? And the names are also same, CSR, RVR, CVR, right? CSR, RVR, CVR, Calip, and Calip. The last thing here is the value of the timeout. So it's a 20, we talked about SysTick being a 24-bit counter, a down counter. So if you see, I have 24 bits that are all set to 1 here. So that is what is happening. So these then again, the .equ is a way of creating friendly names for values, right? Okay, so now what I can use these for is when I'm programming the registers, I can address them by the name. I can use these labels here. Okay, and what I'm going to do now is straight up copy paste the code and then explain what is going on. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9. So there are total 9 lines here. And what, oh, okay, wrong place. Let me go ahead and cut this. So we would want to program the SysTick as part of the reset handler. Okay, so what is going on? I'm saying, okay, in R0, load the number SysTick underscore CSR, which is this number. And my intention is that, let me just, right. My intention is that I'm going to make R0, R1, R2, and R3. So these three, R0, R1, and R2, point to the SysTick related registers. So these are the memory addresses. And then you see this here where I'm using the square brackets. It just means, hey, take the value of R3 and store it at the address that is held by R1. So it would mean that whatever number R1 is holding, and R1 is kind of holding this number here, the hex E000 E01X 48 C or 0, something like that. So whatever is the number that R1 is holding, yeah, use that as a memory address, and in that memory load the value of R3. That is what the square brackets here denote. So again, what I'm doing is R0, R1, and R2, I'm loading the addresses of different registers, and this equal to the number means, hey, take this number, put it in this register, and LDR is load register. That's the instruction. So loading 3 registers with the addresses with bigger numbers that are to be treated as addresses. And then R3 is the value of timeout, which is hex 00FFF, all Fs, right? The 24 bits being set to 1. Now the interesting thing is happening here. So this is where actually SysTick is getting programmed. And we'll see how. So what I'm then saying is at this point is, hey, I want you to issue a store operation, take the value of R3, which is the 24 bits set to 1, the FFFF, and go ahead and write it to whatever R1 is pointing to. Whatever number R1 is having, treat that as an address, go to that address in the memory space, in the address space, so to speak, and then take the value of R3 and put it there. And what is the CSR? Let's check that register once. So what register is CSR? It's the SysTick control and status register. We are storing the value of all ones there, which is interesting. So we are then going ahead and writing 1 to all these 3 places. That's what is happening, I suppose. Yes, the timeout is this, CSR uh, is this, and well, this is really interesting. Oh, okay, RVR. So yes, it was interesting because of what follows. So R1 is the register that is pointing to RVR, not CSR. So we'll go and then take a look at what the RVR register is, and it will be reload value register. Uh, this is the value of timeout. This register holds the value of timeout, and we set everything to 1 here. So the 24-bit are set to 1. It's like value to load into the SysTick CVR register when the counter is enabled and when it reaches 0. So now the interesting bit here is we are to imagine the SysTick's implementation to be like so. So we load a value here, which is all F's, and then there is another register which is kind of reflecting this value. And every time this value reaches 0, the SysTick will issue a interrupt, right? And well, made a mistake there. Just a moment. Okay, too many backspaces. Yes. So we load the value here, which is 24 bits. They are copied into another register, and this is the register that will tick down, that will count down the 24 bits. And as soon as this reaches 0, this register reaches 0, an interrupt is fired or exception is fired. And not only that, when the SysTick handler returns, this value is reloaded back. So this is how the SysTick works, right? And that is what we are going to take advantage of. So this is the register we programmed, and the SysTick current value register, well, it is exactly that register which is counting down. So what will happen is anytime arbitrarily from any part of the code, we want to read the value of the SysTick timer as to how much ticks it has counted. This is the register we read, right? Okay, so now we are not bothered about all of that currently. The RVR is what we are wanting to kind of program. So that is what we program here, all 24 bits. Then we say, hey, load the value of 0 in R3 and then go to the CVR register, which is this, the current value register, and set it to 0, right? So if you see here, it says, hey, reads return the current value of the SysTick counter. When you read this memory location, you get the current value of the SysTick, the countdown. A write of any value clears the field to 0 and also clears the sysTCSR count flag bit to 0. We don't care about this flag yet, but writing anything to this sets it to 0, which is perfect. So what we're then ensuring is that this particular register, the CVR register, is set to 0. And that's about it. So we first loaded the countdown time, then we cleared the live counter register, and then finally what we are going to do is write 111, which is, so to speak, 7, into the status control and status register. Let's see, where is that? So okay, SysTick control and status register. So we are writing 111 here. Now what does that mean? So the count flag returns 1 if the timer counted to 0. Since last time it was red, I think it's immaterial to write 0 or 1 to this. We are choosing to write 1. I think that will be ignored. We are using the processor's clock, so same clock as processors, so this is fine. We are not using external timer. Oh, actually, I just realized we're not even writing or fiddling this with this bit position. So I take back my words. What we're saying is the clock is the processor clock. The count down to 0 that needs to start, or rather, um, when this reaches 0, when the timer reaches the 0, we want an interrupt, we want an exception. And then this 0th bit is essentially saying, hey, enable the SysTick timer, right? So programming these four, 3 or 4 memory locations, 3 of them, right? What is going to happen is the SysTick will start to tick down. And as it starts to tick down, after a certain point, the SysTick handler should be called, right? And to confirm whether or not the SysTick handler gets called, what we are going to do is we are going to use the exception entry and return, one trick from there, or one loophole from there. So when we talk about exception entry and exit, so let me draw a diagram. Okay. So again, we have the CPU, we have the registers, it was merrily executing something. In this case, it would be executing the P dot in the reset handler. And we'll talk about reset handler. We'll talk about why it will do that in a bit, but it will be continuously executing the B dot, and then an exception handler or exception happens and it goes to SysTick. And we talked about the fact that during the entry, it will save certain registers like PC, R4, R3 to R0. It will save those registers and it will not save any other, which means R4 up to R11 are free for us. If we fiddle something there, because that is not saved and restored, the CPU register will stay intact. And just if this is not clear, just give it a deeper thought. Just let's kind of go back to this diagram here. It says during the exception and the return from exception, these are the registers that it will save and restore. And one of the registers that it doesn't save is, let's say, R5. So what we can then do is we can just say, hey, and we can also do that here. We can say, hey, move R5 the value of 0, right? Let's move value of 0 in R5. And why we are doing that becomes clear in a bit. What we'll do every time we hit the SysTick handler is we'll say, hey, what I want to do is just add to R5 the value of R5 and just increment it by 1. So this is our way of now tracking whether or not the SysTick has expired, whether or not this handler is getting called. And you'll shortly see what happens. And just for debug purposes, I'm going to call this breakpoint or break here. You'll see why I'm doing this in a bit. Okay, so we are then all set. What do we have here? We have the vector table that is set correctly. We have the SysTick handler installed. We have the reset handler here. The reset handler programs the SysTick timer and it loops here forever. And after programming, oh, actually, let me do this. Let me move this up just so that we clear R5 first, and then we go on to programming the SysTick, and we are going to loop here forever. All right. And then what we have here, we say, hey, we also have SysTick handler. It only executes one instruction, which is add to R5, well, increment R5 by 1, essentially. And now here we had this B dot, but B dot would mean that it spins there continuously. We don't want that. What we want instead is we want to kind of exit out of an exception handler. And the way to exit out of an exception handler is branch exchange with the link register. So the link register is during the exception entry, What the CPU does is it kind of stores a special value in the linked register to suggest that it has gone to exception handling. So when we are kind of returning back, we have to use this BXLR instruction, which conveys to the CPU that, hey, I'm actually returning, but I'm not returning out of anything that's, let's say, something like a function call. I'm exiting out of an ISR. Long story short, when you want to conclude your ISR, BX space LR is the instruction to use. All right, so we'll save this. Let me then go ahead and do a make. All right, things have compiled and the GDB server has started for us. I'm going to click plus here, get another terminal, grab this and drag it to the editor area, right? And I'm going to now do make GDB. All right, so the processor is kind of waiting for us on the first instruction within the reset handler, and then we are going to kind of do, next instruction. Now, what you'll notice is R0, R1, R2, and R3 will get programmed with the different values, the hex 3000, sorry, E000, E0101418, all of those. The SysTick handler related addresses essentially. Do you see this? When I do NI again, which is next instruction, it'll load R1, then it'll load R2, then it'll load R3. Okay, now what I'm going to do is I'm going to just set a breakpoint, and the way to do that is break. And where am I wanting to set the breakpoint? I'm going to set it here, break here. So we have a breakpoint set. Now let me explain you what will happen next. So I have right now just simply loaded the values, the intended addresses, R0 to R3, R5 is set to 0. Now what I'm going to do is press C. C essentially means, hey, continue to execute until you hit a breakpoint. So it will go ahead and program the SysTick timer registers. The timer will start and, execution will go on for some time, which means it will be at B dot. And then what happens is all of a sudden our breakpoint will be hit. And that confirms that the CPU went from executing the B dot to executing the SysTick handler, right? So let me go ahead and then demo that to you. So when I do a C or continue, it will go ahead and actually execute all of these instructions, and then it'll be stuck here, right? And then I can just quickly demonstrate that. I'm going to do C. So right now it's, when we saw the screen being kind of blank for some time, that is when it was executing the B dot. And now if you notice, we are within the SysTick handler because the timer expired. And when we are in the SysTick handler, just notice that R5 is now incremented by 1. And so next time I do C again, it will kind of continue to continue to execute, which means it will return from the SysTick handler, go back to executing this line, and then after some time get within the SysTick handler again. And then we'll see the value of R5 being incremented by 1. So let me just go ahead and do that. Right, so we have this incremented by 2. So second time, this is the second time the SysTick timer went from the 24-bit all ones value to 0. If I do C again, this is the third time. And now let me do one more thing to prove the point that it was executing the B dot, which is if I press C, hit the return key, and then after that, quickly, if I press Control and C, what will happen is we'll instruct QMU, or we'll instruct GDB to kind of stop the CPU wherever it is and drop the GDB console for us. So let me go ahead and do that. So I'm pressing C, and quickly after this, I'll press Control C. So if you see, when I press the Control C, The control is at line number, or the CPU was at line number 635, and 35 happens to be P dot. So I'll then just go ahead and press C again, continues to execute and drops in the SysTick handler. This is the 4th time, 5th time, 6th time, and so on, 7th time. What should be clear to you at this point, what I was trying to convey? And let me exit the GDB and also QMU, which is Control A, after that X. I just noticed that I don't have, yes, let me pull this here, right? So we have the QMU exited, we have the GDB exited. Let me close all of this. So what have we succeeded in doing right now? We have just programmed the SysTick and ensured that the SysTick fires correctly. So things that we have successfully done: place the correct vector address at the right location in the vector table. We have written an ISR that just counts up the R5 value, and we have programmed the SysTick correctly.